Hi. In this video, we're going to talk about the size requirement reactors for single reaction. Now, before going to the flow reactors, which will be the main focus of our discussion in this particular lecture series, we'll talk briefly about batch reactors. Okay. The batch reactor, as you know, has a very big advantage of small instrumentation requirement. Okay, small instrumentation requirement means it is not a continuous process. So there is no question of automating the entire setup. And when there is no requirement of automation to a very large extent, then we require less number of sensors and less number of instruments to measure the important process variables. Now that cuts down on the instrumentation cost as well. Also, it is having a very flexible operation. It means you can shut down the process anytime you want and you can take it out for cleaning. Then you can easily start up the operation as well. It is totally under the control of the operator. But it also has some disadvantages. One big disadvantage is it is very much labor intensive, so highly labor intensive. Now, since the process is not that much automated, obviously manual labor is required. Although nowadays, you know, given the current industrial phase, the labor intensiveness is slightly cut down, but not to the extent as it is for continuous processes. Okay. Another big factor is the handling cost because once you require more labor, you require the handling to be perfect. Because with machines you can maintain certain criteria, but with operators, especially operators who are not that well trained in the beginning, the handling cost is often very high. Okay. Uh, like I said, there is something called a shutdown time or a startup time. So shutdown means you are completely stopping that process. Maybe you are going for a cleaning of the equipment, or you are going to do some other testing, maybe fault detection testing of the equipment, and so on. After whatever work you are shutting it down for is done, you will be starting up the process. So this shutdown or startup, whichever you are doing, the startup time may not be optimal. Okay, so it may not be as per the requirement of the entire plant. So that can create some gaps in the operations of the entire plant. Okay. Also, quality control on the product is low. Quality control. What do you mean by quality? So you see, this is a bit like story that I would like to share. So let's say you have a batch reactor, okay, and you have already put some fluid in it, and it is giving a particular product. Okay, so let's say I want this product to be 90% pure. Okay, some user criteria is required. So I want it to be 90% pure or 90% selective, right? Now, once I have put this criteria, it is my job to ensure that this criteria is met for all the batches that will be operated. So once this batch is over, you are testing the product criteria. Meanwhile, you are also processing the next batch. Now, suppose during the first test, the result comes that no, it's not reaching exactly 90%, it is coming around 87%. Okay. So even your recipe or the method in which you are going to react and everything, all the operating conditions are set and so on, you have already processed another batch which will give you 87% of the specifications. So that creates a problem. quality control becomes very tough. And right now, in 2024, a lot of research is being considered for the quality control of batch processes in general. By batch processes, I just do not mean batch reaction, but batch separation processes as so. That is a huge thing about batch reactors. The quality control is a very big factor. Now, given all these points, we will like to generalize that batch reactor is very well suited for specific operations where you are dealing with very small amounts of material, and you want to have selected products from a single equipment. Okay, but for if you have a large process to handle, a large mm, demand to cater to, in that case continuous processing is the way to go. Now coming to the sizes of batch reactors. Batch reactor, if you remember, in the previous videos I have already spoken about the time requirement for a batch to be processed in case we consider the ideal batch reactor. So you may have seen this equation that the time is expressed as Ca0, 0 to Xa dxa by minus Ra. Let me explain what these terms are. So T is the batch time, okay. Ca0 is the reactant concentration at T equals to 0, that is at the starting time. Xa is the conversion of A, and minus Ra is the consumption kinetics equation of A. Okay, so I'm just considering a very basic single reaction, just A gives product. So with respect to that, I have written this expression. This is the expression to understand that what is the time required to achieve a certain concentration Xa in an ideal batch reactor. Okay, and this is valid for the constant density system. So I am considering that the volume ratio of A remains 0 throughout. Okay, this is the volume ratio. Let me write it. Volume, sorry, let me just erase this. Volume ratio. Okay, this is the time required. If you consider this equation and you compare for the same criteria of a plug flow reactor, that is the space time required to process the volume of reacting fluid to get a desired conversion, then you will get an expression like this: tau equals to Ca0, 0 to Xaf dxa by minus Ra. This expression is for batch reactor, and this is for a plug flow reactor or PFR. This time over here is the batch time, and this tau over here is the space time. That is the time required to process one volume of the reacting fluid. Okay, so if you consider these two, they are almost you know similar to characterize. Therefore, for a given duty, for a given reactor duty, by reactor duty I mean the task that is to be done using that reactor. So for a given reactor duty and considering a constant density system, the performance criteria for the plug flow reactor and the batch reactor becomes the same. That is, they take the same length of time or the same amount of time to process the reaction volume. Therefore, what happens? The same volume of these reactors will also be required. Okay, remember that this is in considering that it is a constant density system. If it is not a constant density system, then you have to go through further calculations, but that is beyond the scope of this discussion. So sticking to the constant density system, the performance equations for batch reactor and the plug flow reactor gives the same understanding of the process, and therefore we can say the volume of batch reactor will become equal to volume of the plug flow reactor. Remember, strictly it's for a constant density system. Okay, but in case for a very long term production, we may have to correct the size requirement to, you know, take into consideration the shutdown and startup criteria in between the batches. So keeping that apart, the batch reactor volume and the plug flow reactor volume becomes the same for the constant density system. Next, we will be discussing about the uh, flow reactors or the continuous reactors. That is it. Thank you.